Hi friends, today we are gonna continue with the lab 3.6. In this lab, we are gonna continue with the uh, examination of our model, and we are gonna evaluate our model if it's necessary, and how our model actually work. Uh, we are gonna see that, and to see that, we will just do the same things as we did in lab 3.5. We are gonna extract our data, and we import the necessary libraries, and we are gonna map our data. We are gonna convert it pandas data frame. We create a test and validation channels, and we are gonna continue with the creating an predictor and XGBoost. So I'm just gonna run these parts. We have done it before, so let me just run these parts. And now it's training our job, and while it's training, we can continue from here. As we did in the last lab, uh, we are determining a threshold, and if any of the data is predicted data is higher than this threshold, we are labeling this data as abnormal, and if it's lower than the threshold, the it becomes the normal case. And what we what we will do in this lab, we are gonna create a confusion matrix to see how well our model is performing. The confusion matrix is simply looks like that, and there is a predicted prediction is seeing in here, and the actual values are being here. This 7 is giving us the true positive, so the prediction is true with the actual value, and this is giving us the uh, false positive, true positive, false positive. Actually, I could be wrong, and yeah, here is a true negative, true post, true negative, true positive, false false negative, false positive. Yeah, it gives us a true positive, false positive, true negative, true false negative, and false positive. Uh, it's a little bit complex for me. The confusion matrix make a confusion on my mind. Anyway, and based on these values, we are gonna see how well our data is performing. So, for example, let me give you an example. We want to determine an illness, and for example, 5 people out of a million people is sick in our case. These are our actual value, and our our model is says that nobody is sick, and 1 million people out of 1 million people is not sick, and the correctness of the algorithm should be very high. But it, it is that means that our algorithm is good? No, because what we want to do, the uh, illness is so rare to catch. So we want to increase the sensitivity of our algorithm, which I give the example says that the sensitivity would be 0, and there is also specificity. So for example, we are trying to uh, create an illness detection mission, and uh, this mission could be so sensitive, and when it says that a person is sick, the person could be 100 out of 100 could be sick, but it doesn't mean that maybe this machine could miss some people. For example, if we choose this threshold, for example 0.9, 0.9, and the data will return us, for example 0. 0.695, and the the people in here, in our cases, the people uh, should be, or have to be, actually have to be sick, because the threshold is so high, and when we increase this threshold, the sensitivity will be more higher than before. But when we actually instead of 9, we can say in here 7. So in that cases, for example, there is a patient, and this patient's return the prediction value is 0.85, and this patient is actual positive, so is sick actually. But in the before example, we miss that people actually is cancer or ill, but we say that for that person you are not ill, so we miss some of the people in here. So it we can choose a balance between the specificity and sensitivity, or we can increase the sensitivity. It depends of the what works we are doing. So we can choose whether increase sensitivity, we can choose whether increase specificity, or we can choose a balanced way to make them a half, for example. And that's all for explanation before the training job. I'm just gonna check the training job completed or not. The training job is completed, and there is a batch transform jobs, because we are doing at the same time a test and validation in here. So we need to wait for it, and it will be done soon. I'm just gonna pause the record, and when it's done, I'm gonna continue from here. So uh, it's finished, and now we're gonna continue from here. Now, as returning us all the values in first 5 data, all of them are uh, abnormal, but in the actual data, the second one is not abnormal. Actually, it needs to be normal. Now, as I said earlier, we are gonna create an confusion matrix, and let me continue from here. Yeah, now it's created an confusion matrix, and I think that's okay. Yeah, and as I said earlier, this is true. This is true positive, false positive, false negative, and these are the true negatives, true abnormal cases. Now we are gonna continue from here. This is our predicted class, and these are our actual cases. Actual cases is shown in here. So we have truly predicted are 7, and these many people are predicted correctly. Now I'm gonna continue from here. So the true negatives are 7, as I said, and false positives are 3, true negative, false positive, false negatives, and this gives us false negatives 2, and true positives. This here is true positives. I think I could say wrong, but it's not so important. If you understand now, that's okay. Now we will gonna check the sensitivity to calculate the sensitivity. We use this formula in here: true positive divided by true positive plus false negative. And let me check the sensitivity. Sensitivity could be now low. I'm not sure. It's about 90%, 90 and a half percent. Now let me check the specificity. The specificity is 70%, and we are gonna positive and negative predict values to see that. We divide the true positive or divided by true positive for positive precisions and recall. So it's our precision, and the negative predicted value is the proportion of negative results. So true negative plus false negative. So when we run that, it will give us this many percentage. And I'm going to continue with the false positive rate. What's the false positive rate? as 30 percentage. Let me check. And what was positive to find? We use false positive divided by false positive and true negative. So false positives are false positives are 3, and true negatives are 7. True negatives and false positives, and it returns us the ratio of the false positive. And to check the false negative, it run here. It should be lower than this value, yeah, because it's almost 19 people. 19 data is corrected true. Now we are gonna check the false discovery rate here. False discovery rate is 13 percentage almost. And how accurate is your model? So overall accuracy, I'm gonna check. The overall accuracy is 83 percentage, and this will all give us what we have done in the above. Yeah, we can see uh, all the results in here. Before calculating the area curve, and I just want to change these where was it? This the threshold. I want to change the threshold. Yeah, it's here. I want to make the threshold 8. No, I want to run this one. Yeah, now for example it's determined here, and I want to create a confusion matrix. In that cases, as you can see, it's now says the uh, the uh, the the true positives, the abnormal cases is true positive. The true positives are now decreased because when I have explained already. I'm not gonna say the sick people. It says the a person could be abnormal, but it misses because the sensitivity is so high in that cases. Let me just run these parts, and to show you the sensitivity and specificity. I most probably specificity will decrease and sensitivity will be higher than that value. Actually, it decreased because it it it's I don't know why the specificity comes same true positive, true positive plus false negative, plus false negative. So true positive, true positive plus, false negative. False negatives are 5. I want to make it even more higher than that. What will happen now? I want to see the create a confusion matrix. It's now mm, it's now worse than before. It will give lower than that value. How? I'm not sure because we have the two positive, false negative, two positive plus false negative. So false negatives are visits here. Yeah, it became 6. When I did here as 3, 1, 1, it came. I want to see. It's becomes 2, so 3 is better than 9 or 8. We can determine the threshold by the, the data returns values. So actually I increased the specificity, I decreased the sensitivity when the threshold becomes higher. Yeah, yeah, because the I get it now because the true positives are showing in here that we, because we says the abnormal cases as 1 and and we showing the true positives in here and the false positives in not false positive, true negatives in here. If we should we if we would show the true positives in here, the sensitivity would becomes much higher and the specificity would become less. Anyway, I'm gonna just continue from the last part. I'm just gonna run here. These are showing televisions. And I actually don't remember how to analyze these graphs. I don't remember. Sorry, guys. Actually, I'm just gonna read here. The higher the area under the curve, the better the model is at distinguish between abnormal and normal patients. Depending on the value you set for a threshold, the area under the curve can change. You can plot area under the curve by using probability zero class. Is that threshold. Depending on that threshold, we have here. Hmm, I'm not sure. Just just run it again. No, that's not just threshold. Confusion matrix. It gives one parameters. State predicted. Target predicted. Test labels. So yeah, I'm not sure. Nine. That's not about threshold. Let me find. Burns. Nothing. Confusion matrix. Target. Anyway, I'm just gonna stop this lab in here. I just don't know. I just don't remember. I need to check is area under the curve and walk curve. And thank you for listening to me. See you in the next lab.